Well, welcome to our seminar tonight on electrical and basic electronics. This is designed to be a review. My assumption is that you've seen the vast majority of this material somewhere along the line, and I just hope to kind of refresh your memory in the next couple of hours of some of the basics that you may have to know in order to pass acceptance tests into these employers. So here we go. All right, the first thing we're going to talk about this evening is waveforms, different sorts of waveforms. And the first waveform we want to mention is a basic steady-state DC waveform. You see one on the screen here. It remains either positive or negative throughout. It never swings across the 0-volt line. That defines a DC waveform. And this is a steady-state waveform. It never changes its value. And this is a voltage waveform you see on the screen. Now, AC waveforms are both positive and negative. That's their definition. Alternating current waveforms are both positive and negative. And you see a sine wave on the screen in front of you. There's a few characteristics of sine waves that I thought we might ought to go over. First of all, the maximum value of this particular waveform is a voltage sine wave. The maximum value of this voltage sine wave is called the amplitude or the peak voltage. And peak-to-peak voltage is the maximum to the minimum. And generally that's twice the peak voltage if the sine wave is centered around the 0-volt axis like this sine wave is. A cycle of a sine wave is 360 degrees, or if you look at the waveform, it's where the sine wave begins to actually repeat itself. And the period is how long it takes for a sine wave to complete one cycle. That would be in seconds, or in this case, milliseconds. All right, all these waveforms you see, even though some of them look kind of funky, they're all AC waveforms. Okay, the first one is a sine wave. The second one is kind of a convoluted sine wave. It's made up of actually several waveforms that are combined. The one right below that is a triangle wave, and the next one's a square wave. And all these are considered to be AC waveforms because they swing both positive and negative. Now, you can take an AC waveform shown at the top of the screen and rectify it with a diode rectifier and come out with a half-wave rectified DC waveform. Now, the waveform at the bottom doesn't really look like DC, but it is DC because it never crosses the 0-volt line and never swings negative. It remains positive the whole time, even though it's a chopped waveform. You can take that same AC waveform and run it through a 4-diode bridge-type rectifier and have a fully rectified AC waveform that you see at the bottom of the page there, the DC out. Again, that may not look a whole lot like a DC, but it is definitely DC because the waveform is positive the entire time. It never swings across the 0-volt axis, never goes negative. One of the waveforms that those of us that work in industry have to deal with is called a pulse width modulated waveform. This is the waveform that a variable frequency drive or an inverter drive puts out. It uses this waveform to control the speed of AC motors. We're going to talk about AC motors a little bit later, but the speed of an AC motor is controlled by the frequency of the input waveform. So if you can vary the frequency, you can vary the speed. Pulse width modulated waveforms are strange-looking waveforms. They're made up of pulse width modulated, in other words, varying pulse width waveforms in the positive half and then varying pulse width waveforms in the negative half. And if you were to look at the area under the curve, the integration of this waveform, you'd see that it would form basically a sine wave. And motors are pretty dumb things. You can put one of these chopped up waveforms that swings positive and then goes negative and has different widths into a motor, and it'll think it's a sine wave that's actually controlling it. To the motor, it simulates an AC sine wave. This is called a pulse width modulated waveform. All right, enough on waveform. Let's take a look at some basic DC circuits. The first DC circuit that I want to talk about is a series circuit. And the characteristic of a series circuit is the same current flows through all elements. That kind of defines a DC series circuit, is the same current flows through all the elements. Now, if we wanted to take a look at this particular waveform and find out some of the characteristics, this circuit, and look at some of the characteristics of it, first thing let's do is find the total resistance as seen by the battery. Well, the total resistance is made up of the addition of the resistors. Resistors in series just simply add. So the total resistance as seen by the battery is equal to R1 plus R2 plus R3. Well, R1 is 1.2 K ohms, or 1,200 ohms. R2 is 3,300 ohms, and R3 is 680 ohms. If I add those three values together, I come up with 5,180 ohms. That is the total resistance as seen by the battery. To find how much current flows in this circuit through each of the elements, we can use an Ohm's law relationship. Voltage equals current times resistance, or in this case, current is equal to voltage divided by resistance. And the voltage would be the battery voltage divided by the total resistance as seen by the battery. So we take 10 volts and divide it by 5,180 ohms. Comes out to be 1.93 milliamp. A milliamp's 10 to the minus third amps. So 1.93 times 10 to the minus 3 amps. Now, we can find out how much of that voltage, that 10 volts, is dropped across R1 by using that same Ohm's law relationship. The voltage across R1 is equal to the current that flows through R1, which is I sub t, same current that flows through all of the elements, times R1. So 1.93 milliamps times 1.2 K ohms tells us the voltage drop across R1 is 2.317 volts. So if I took a voltmeter and placed it across R1, I would read 2.317 volts. Of the 10 volts, 2.317 drops across R1. The rest of it has to drop across R2 and R3, of course. If I want to find the power dissipated in resistor R1, power is equal to voltage times current. We just calculated the voltage drop across R1, 2.317 volts. If I multiply that by the current in this circuit, 1.93 milliamps, I come out with 4.47 milliwatts, times 10 to the minus 3 watts, in other words. I could also use I squared R. I squared R would give me exactly the same answer, 4.47 milliwatts. Well, we might be interested to know how much power the battery has to put out in order to provide current in this circuit. And the power that the battery produces is equal to the voltage drop produced by the battery, 10 volts, times total circuit current. So 10 times 1.93 milliamps turns out to be 19.3 milliwatts is what the battery has to produce, 19.3 milliwatts. So there's a series DC circuit. Let's take a look at a parallel DC circuit. The characteristics of parallel circuits are the voltage drop across all elements is the same, whereas with a series circuit, the current flow through all elements is the same. To find the value of resistors in parallel, 1 over the total resistance is equal to 1 over R1 plus 1 over R2 plus 1 over R3, and if there was more resistors, it'd be 1 over R whatever. Okay, so 1 over the total resistance equals 1 over R1, 1/90th, plus 1 over R2, 1/45th, plus 1 over R3 is equal to 0.3888. Now that's 1 over RT. So to solve that equation for RT, I need to take 1 over that value. 1 over 0.03888 equals 25.71 ohms. That's the total resistance as seen by the 9-volt battery. I could replace R1, R2, and R3 with a resistor of 25.71 ohms, and the battery wouldn't know the difference. One thing about resistors in parallel, the total equivalent resistance has to be less than the smallest resistor in parallel. Well, the smallest resistor in parallel is 45 ohms, and 25.71 is less than that, so it makes sense. The total resistance, 25.71 ohms, it makes logical sense. If we came out with 200 ohms or something, we'd know we'd messed up somewhere in the math. That's just a good check. Okay, so the equivalent resistance, 25.71 ohms, the battery current, the current that leaves the battery, is going to be the voltage drop across the battery, the voltage produced by the battery, 9 divided by that total resistance is 0.35 amperes, or 350 milliamps. If we wanted to find the voltage drop across any of those elements, because they're all in parallel, they're all 9 volts. The voltage drop across R1 equals the voltage drop across R2 equals the voltage drop across R3 equals 9 volts. Suppose I wanted to know what the current flow through resistor R1 was. Well, we know the voltage drop across R1, and we know the value of R1 is 90 ohms. So we can use Ohm's law and say that the current flow through R1 is equal to the voltage drop across R1, 9 volts, divided by R1, 90 ohms. That turns out to be 0.1 amps of current flows through R1. Suppose we wanted to find out how much power how much power was dissipated across R1. What's the power that R1 has to dissipate in heat? Of course, that's how resistors produce power, is by heat. We could use the power dissipated by resistor R1 is equal to the voltage across R1 times the current flow through R1. P is equal to V times I. And we know both those quantities. 9 volts times 0.1 amps is 0.9 watts. Again, we could use I squared R here too. 0.1 squared times R, and we get the same answer. Okay. So there's an example of a DC parallel circuit. Now, if we look at some of the other elements you may find in circuits, such as inductors and capacitors. Inductors, in this circuit, you see L1 is the inductor, and a characteristic of an inductor is it looks like a short circuit or a piece of wire to DC. So in this particular circuit with a 12-volt battery, L1 may as well not even exist. It might as well just be a piece of wire, okay, that connects R2 to the bottom rung. All right? And capacitors look like open circuits so that no current flows through any branch in a DC circuit that contains a capacitor. Those are handy little tidbits of information to know. Inductors look like short circuits to DC. Capacitors look like open circuits to DC. All right, let's move on to AC circuits. We mentioned inductors a minute ago. Down at the bottom of this page, on the left side, you see the schematic representation of an inductor. And on the right, you see an actual inductor. It's just a wound core. It's got a core with wire wrapped around it. That's how you make an inductor. Inductors present what's called impedance, Z sub L, to AC current flow. And the impedance of inductors is called inductive reactance. And the equation for inductive reactance, X sub L, is equal to 2 pi FL. And pi, of course, is a button on your calculator, approximately 3.1416. F is the frequency, and L would be the inductance of the inductor in henries. We'll use this equation in a few minutes. Inductive reactance has a phase angle associated with it that's 90 degrees out of phase with resistance and 180 degrees out of phase with capacitive reactance. And like we said earlier, inductors appear to be short circuits to DC. Capacitors. On the lower left, you see the schematic symbol for a capacitor. And over to the right, you see a couple of actual electrolytic capacitors. Capacitors also present impedance. Their symbol is Z sub C to AC current flow, and the impedance presented by a capacitor is called capacitive reactance. The equation that describes capacitive reactance is X sub C is equal to 1 divided by 2 pi FC, where again pi is a number on your calculator, 3.1416 approximately. F is the frequency, and C is the capacitance in farads. Again, we'll use this equation in a minute. Capacitive reactance has a phase angle associated with it that is 90 degrees out of phase with resistance and 180 degrees out of phase with inductive reactance. And like we said earlier, capacitive appear as open circuits to DC. Now let's work a problem. Okay, and you see the problem here. It's an AC circuit problem. It has an AC source of 1 volt amplitude and a frequency of 60 hertz. I've got a resistance, R1, of 100 ohms. I've got a capacitor, C1, of 10 microfarads. I've got an inductor, L1, of 100 millihenries, 10 to the minus third henries. And, of course, a microfarad is times 10 to the minus sixth farads. I'm going to take this problem, and what I'm going to solve for is how much current flows. Find the magnitude of the current in this circuit. Okay, we're given the capacitance, we're given the inductance. The first thing we need to do is find the impedance presented by those elements to the current flow. So capacitive reactance, like we said a minute ago, is 1 divided by 2 pi FC. All right, I plug the values into that. I get 1 divided by 2 times pi times F is 60. C is 10 times 10 to the minus 6. Be careful on that calculator crunch, by the way. It's 1 divided by that quantity. Make certain you put parentheses around the quantity when you do that math. If you punch that into your calculator, it should come out to 265.26 ohms. That's the impedance presented by the capacitor to that AC source. The inductive reactance is 2 pi FL. Plug in the numbers. 2 times pi times F is 60. L is 100 times 10 to the minus third. Plug it into your calculator. You should come up with about 37.7 ohms. All right. Now, recalling that we just talked about the fact that the capacitive reactance and the inductive reactance are 180 degrees out of phase with each other. We have to add these what's called vectorially. They have not only magnitude, they've got direction. Okay, so when you add two things together that are 180 degrees out of phase with each other, in effect what you're doing is subtracting one from the other. So the equivalent reactance of the capacitor and the inductance is the difference between them, 265.26, which was the capacitive reactance, minus 37.7, which was the inductive reactance. That turns out to be 227.56 ohms. That's the equivalent reactance of adding the capacitive reactance and the inductive reactance together vectorially, 180 degrees out of phase with each other. Now, step 3, since resistance and reactance are 90 degrees out of phase with each other, we must again add them vectorially. And since they're 90 degrees out of phase with each other, the best way to do that is to consider them to be sides of a right triangle. Adjacent side for the resistance, opposite side for the equivalent reactance. So if we add those together squared under the radical, that's the Pythagorean theorem, square root of R1 squared plus X equivalent squared. That's using the Pythagorean theorem to solve for the equivalent, or the hypotenuse in this case on the triangle. That's square root of 100 squared plus 227.56 squared. We do that math carefully. We come up with 248.56 ohms for the total impedance as seen by the source, considering the resistance, the capacitance, and the inductance. Now we were asked to find the total circuit current. Since we now know the total impedance as seen by the source, we can just use Ohm's law for AC circuits and say that the current equals the voltage divided by the total circuit impedance. That's 1 divided by 248.56. 4.02 milliamps is how much current will flow in this circuit. 4.02 milliamps of AC current flow. So there's a good example of AC circuits using a series circuit. All right, let's keep moving. Let's take a look at section 4 on meters. One of the most common meters people have to use are voltmeters, and what they do is they measure voltage across elements. So you connect them in parallel with the voltage to be measured, or across the element that you want to be measuring. Voltmeters are connected in parallel, and voltmeters, by their very construction, have a very high impedance because you wouldn't want to connect a voltmeter into a circuit and have it affect the way the circuit worked. So they offer high impedance to current flow so that they don't affect the way the circuit works. Now, ammeters, on the other hand, measure current flow in a circuit. You connect an ammeter in series, and again, since the ammeter is part of the circuit, you don't want it to affect the way the circuit would normally operate, so these have very low impedance to current flow. Very low impedance devices, ammeters are. They're connected in series. Ohm meters are used to measure the resistance of a circuit, and you place the ohm meter in parallel to the element or across the element to be measured. In the example on the left at the bottom there, you see a resistance, and you're measuring the resistance of that resistor using an ohm meter. Another specialized type of meter is called a megohm meter, or a megger. These are meters that are used to test insulation. You want to verify the condition of insulation of conductors or motors or other electrical devices, you use a megger. What they do is they inject a high voltage, anywhere from 500 to 1,000 volts, and then they measure the current flow. And then they just use an Ohm's law relationship to determine the resistance, where resistance equals voltage divided by current. We'll talk more about meggers in a few minutes. All right, let's keep moving. Let's talk about AC motors. The most common type of AC motor in industry is a three-phase squirrel cage induction motor. These are the workhorse of industry. There's many, many more three-phase squirrel cage induction motors than any other type of motor in modern industry. They consist of a set of windings embedded in the stator. That's what you see on the left. That's the housing. And then they also have a rotor that's made up of bars that are connected together at each end by what are called shorting rings. You can see that on the lower right. You have bars that are connected together, and they're shorted out at the end by shorting rings. That's how induction motor rotors are constructed. How do they work? Well, three-phase squirrel cage induction motors operate by applying a three-phase waveform to the stator, and when you apply the three-phase waveform, it sets up a rotating magnetic field. And you can kind of see that in the illustration below. You see a three-phase AC waveform being applied, and you can see at the rotating magnetic field in the three views below the waveform. At time t equals 0, the net waveform is vertical at 0 degrees. And then you notice at time t equals 1, which is when B is peaking, it is rotated 120 degrees to the left, counterclockwise. And then at time t equals 2, it is rotated another 120 degrees to, now it's pointing at the vector C. So this particular rotating magnetic waveform rotates counterclockwise when this waveform is applied in this phase sequence, ABC. When you apply the three-phase waveform to the stator of an AC induction motor, it produces a rotating magnetic field. In order to produce torque in a three-phase motor, you got to have two things. First, you have to have generator action. When generator action is established, then motor action quickly follows. Generator action occurs when you have the following. You have to have a conductor. In this case, the conductor would be the rotor bars. You have to have a magnetic field. In this case, the magnetic field is from the stator when I apply the three-phase waveform. And then generator action occurs when you have relative motion between the two. And the relative motion comes from the fact that the rotating magnetic field is occurring in the stator. So now we've established the conditions for generator action. Generator action produces a voltage across the rotor bars, which in turn creates current flow. Why? Because you have a complete circuit for current to flow because of the shorting rings. If you didn't short the rotor bars out at the end, you'd never have any torque developed, never have any motor action occur. Generator action produces the voltage, which in turn creates the current flow in the rotor due to the complete circuit between the rotor bars and the shorting rings. Now we've met the conditions for motor action. Motor action is torque or rotation of the rotor. And that occurs when you have the following. You have to have current flow in a conductor, which in this case would be the rotor bars. We've now established that we have current flow in the rotor bars due to the complete circuit formed by the shorting rings. And you also have to have a magnetic field, which, again, the rotor is in the magnetic field produced in the stator winding. So now the combination of current flow through the rotor bars and the magnetic field produced in the stator causes the rotor to turn. We've created the conditions for motor action. So now I produce a torque in the motor. That's how three-phase AC squirrel cage induction motors work, through generator action followed by motor action. Now, there has to be relative motion between the rotor bars and the rotating magnetic field in order to produce generator action. If there's not relative motion between the rotor bars and the rotating magnetic field, if they're turning at exactly the same speed, you're not going to produce generator action, and then which means you're not going to produce motor action. What this means is the rotor can never turn as fast as the rotating magnetic field. The rotating magnetic field turns at a speed called synchronous speed, and the rotor turns at a speed which is slower than the rotating magnetic field. And the difference between rotor speed and synchronous speed is called slip. And a typical two-pole squirrel cage induction motor at 60 hertz will produce a synchronous speed of 3,600 RPMs, and the rotor will turn somewhere around 3525, 3550. So there'll be 50 to 75 RPMs of slip. The equation for synchronous speed, that's the speed that the rotating magnetic field rotates, is found by this equation. Synchronous speed is 120 times F divided by the number of poles. Now, I gave you an example a minute ago of a two-pole motor. For a four-pole motor, you can plug into this equation and find out what the synchronous speed will be. It's going to be 120 times the frequency at 60 hertz divided by the number of poles. It's a four-pole motor, so divided by 4. That tells us the synchronous speed is 1,800 RPMs. Now, the rotor has to turn slower than this due to slip, so typical four-pole motor rotor would probably be around 1725 to 1750 RPMs. Now, there's a number of varieties of three-phase squirrel cage induction motors. A lot of times you'll find them where they're wired to operate at two different voltages. And what they'll do is bring all 9 leads out to the motor junction box. Now, it's interesting to note that you see the connections here. The one on the left is a Y-connected motor, and the one on the right is a delta-connected motor. And these are connected internally, either Y or delta, as the motor is constructed. But it's interesting to note that the high voltage connection is the same for the Y and for the delta. In order to use the Y in a high voltage connection, I need to series the windings and make them one big Y. So I'll connect 4 to 7, 5 to 8, and 6 to 9. So I've just seried these windings together. Then I'll bring my power in on 1, 2, and 3. Same thing on the delta connected motor. For the high voltage connection, I need to series the windings. So I connect 4 to 7, 5 to 8, 6 to 9, bring my power in on 1, 2, and 3. And that's shown in these connection drawings right below. 4, 7, 5, 8, 6, 9, power in on 1, 2, 3. It doesn't matter if it's a Y or a delta connected motor. Now, that's not true for the low voltage connection. For the low voltage connection, I need to put the windings in parallel, not in series with each other. And there's a significant difference. You can see the connections here. For the low voltage Y, you connect 4, 5, and 6 together. What that does, 4, 5, and 6, it forms the center of another star. And then you bring all your power in on the parallel combination. You bring it in on 3 and 9, 2 and 8, 1 and 7. And for the low voltage connection for the delta, I need to connect these things in parallel, so I have to bring in my power to 1, 7, and 6, 3, 5, and 9, 2, 4, and 8. And that's how the low voltage connection for a delta connected motor would be. Now, to reverse the direction rotation of a three-phase induction motor, all you have to do is reverse the direction of the rotating magnetic field. If the rotating magnetic field goes in the opposite direction, the motor will turn in the opposite direction. So, in order to make the rotating magnetic field go in the opposite direction, you just have to swap any 2 incoming power leads. Now, if a motor is operating along, goes into some kind of a condition where a winding burns up or a fuse blows, or in this case, anything that happens where one of the phases is lost, usually the motor will continue to run, but it's going to vibrate, it's going to run rough. This is called single phasing of the motor. The roughness is due to the uneven magnetic field being applied to the stator. It doesn't have 3 phases applying it, it just has 2 phases and then an opening. So it's not an even magnetic field being applied. The motor will oftentimes continue to run, it'll vibrate, it'll run rough, and it can't operate at anywhere near its full rated horsepower and torque. The current flow in the remaining phases goes up. Sometimes that'll cause another fuse to blow, and then the motor will stop running. Now, it's interesting to note the units of horsepower, or what is a horsepower? It's a unit of power. Horsepower is a unit of power. And so is watts. Watts is a unit of power. And there's a relationship between horsepower and watts, and you see it here in the equation. 1 horsepower is equal to 746 watts. That's a good little number to stick in your back pocket, 746 watts per horsepower. So if I wanted to know what the equivalent wattage for a 20 horsepower three-phase induction motor would be, that would be, well, if there's 746 watts per horsepower and I got 20 horsepower, I'll just multiply 20 times 746, and I come up with 14,920 watts, or 14.92 kW. It's interesting also, in Europe you buy your motors rated in kW. They're not rated in horsepower, but it's the same thing. It's just a relationship between horsepower and watts of 746 watts per horsepower. With Section 6, we're going to be taking a look at AC single-phase motors. AC single-phase motors, the most common type AC single-phase motor, has 2 sets of windings. It has a start winding with a capacitor in series with it, and a run winding. These are called capacitor start motors, and you see a schematic drawing for one on the page here. You have an AC input. You have a capacitor in series with the start winding. This is the start switch. This is the run winding. The winding with the 1 next to it is the run winding. The winding with the 2 next to it is the start winding, and this is called the starting switch. Now, the start winding only has power flow through it until the motor starts turning, okay? And there's a centrifugal switch that opens. That's that starting winding switch after the motor starts turning. How they operate, how they start, is there's a phase shift in the start winding relative to the run winding in both the current and the magnetic flux produced by adding that capacitor in series with the start winding. That creates a phase difference between the start winding and the run winding. The start winding also has a lot smaller wire than the run winding. If it has smaller wire, it has more resistance. So the start winding looks more resistive and capacitive. The run winding looks more inductive. So you can see how there'd be a phase difference between the two. Now, the rotor starts turning due to the simulated rotating magnetic field, which is created from the phase difference between this start winding and run winding. You apply a single-phase waveform, the rotor starts turning. And then as soon as it starts turning, the start winding drops out from this centrifugal switch. Once that start winding is dropped out, it's operating on the run winding only. The rotor just continues to rotate just due to the alternating magnetic field that's produced from the waveform in the run winding. And you can see a picture of a typical centrifugal switch there, that once the rotor starts turning, the contacts come open and it breaks circuit with the start winding. Okay, single-phase motors, capacitor used on capacitor start AC single-phase motors is called an electrolytic type of capacitor. Usually electrolytic capacitors are polarized. They have to be put into the circuit in the right direction, positive and negative. However, motor starting capacitors are not polarized because it's an AC waveform that's going to be passing through them. And you can put them in either way, with either lead connected to the terminals. And there you see an AC single-phase motor, a big lump on the side, a big bump on the sides where the starting capacitor goes. And here's a couple starting capacitors. There's what they look like. All right, moving on, DC motors. A bunch of different types of DC motors. I want to talk about the most common types, which are the shunt motor, the series motor, and then the compound motor. Shunt, by the way, means parallel. So a shunt motor, if you look at the schematic, the shunt field, the parallel field, the field for this motor is in parallel with the armature. And the armature is made up of the rotor, which is fed current through brushes and commutator segments. Okay, so there's current flow in the armature, which is fed by the commutator segments, and the shunt field is in parallel with the armature. Shunt wound DC motors have the following characteristics. They've got what's called excellent speed regulation. And speed regulation is sort of like when you load the motor down, how does it perform? Does it slow down a lot when you load the motor down? If not, if the motor maintains a relatively constant speed, then we would call that excellent speed regulation. Shunt wound motors have a characteristic of having decreased torque when you speed them up. And the reason for that is the armature resistance and the armature reaction which occurs. The field coil is usually smaller conductors than the armature current. The armature conductors are larger. They have to pass starting and run currents. When the motor starts turning, what limits current flow in the DC motor is counter electromotive force or generator action, and that limits the armature current to a reasonable value. What limits armature current when the motor first starts is simply the resistance of the armature. So as it starts turning, counter electromotive force is generated and the current comes down. All right, the next type of DC motor we're going to talk about quickly is the series wound DC motor. In this case, the field is in series with the armature, whereas the shunt motor, the field was in parallel with the armature. They've got the following characteristics. Series wound DC motors have very large starting torques, but they've got incredibly poor speed regulation. If you run one of these things unloaded, they'll literally fly apart. They'll self-destruct. One of the good things about a series wound DC motor is they can operate on either AC or DC power sources. They're called a universal motor. One of the best examples of a series wound DC motor is the starter motor on your car. Now you think about it, a starter motor is a very small little DC motor, yet it has enough torque to be able to turn over a V8 engine, a very large starting torque. So it's a great application for a series wound DC motor. It never operates unloaded, and it's capable of turning over the engine because of its very large starting torque. Now, if we combine the shunt motor and the series motor, we end up with what's called a compound motor. Compound motors are the most common type. They actually have the best characteristics of both the series and the shunt motor. They've got good starting torque, and they've got good speed control. And there's kind of two different types of compound motors. The long shunt has the shunt field in parallel with the series combination of the series field and the armature. So the long shunt, the long field shunt goes all the way across the series combination, where the short shunt only is in parallel with the armature, and then that parallel combination is in series with the series field. So those are two different types of compound motors. They have both shunt fields and series fields. Good starting torque, good speed regulation. Now, interpoles are oftentimes used in DC motors, and they're connected in series with the armature. The interpoles are wired in series with the armature, as you see in that top drawing. The reason interpoles are used is because of this phenomenon called armature reaction. Armature reaction is the bending of the magnetic flux across the main field poles, and it's due to the interaction of the rotating magnetic field and the armature. Now, if you look at the bottom drawing here, you've got a main field north and south. When you put a rotating magnetic field in the middle here, this is a current flow in the armature, so you're going to have magnetic field produced in the armature. What it does is it takes this field, which normally would go straight across from north to south, and it causes it to bend. It bends in the direction of the rotation. So what we want to do is we want to commutate, or have the commutator set in the position which is called the neutral plane. And the neutral plane is always 90 degrees from the main field flux. And if it was straight across, then you'd want to commutate 90 degrees from it, right here where this north and south magnets are shown. However, due to armature reaction, the bending of the flux, you can't commutate there, and by the way, this changes with the load on this motor. If the motor's heavily loaded, then it's going to have more current flow in the armature, and you're going to have more armature reaction occur. So what that means is the neutral plane shifts around all over the place, okay, and then that causes you not to commutate in the neutral plane. Well, if you don't commutate in the neutral plane, you have a lot of arcing and sparking that takes place at the brushes and the commutator segments. It destroys the commutator segments and burns up the brushes, so not a good thing. So you put an interpole in there, and the interpole basically, when the magnetic flux from the armature goes up, since the interpole is in series with it, the magnetic field strength in the interpole goes up, and it just cancels out the bending and twisting of the magnetic flux due to armature reaction. So almost all DC motors have interpoles in them. Okay, and they're small poles that are placed 90 degrees from the main field poles. Let's take a look at some motor circuits. Now we're getting into some fun stuff here. This is a basic motor control circuit. L1 on the left side. Let's follow up a current flow through. Start with L1. We go through a normally closed stop button. And then we come over here to a normally open start button. And then we come to a normally closed contact. This contact is associated with the M2 coil. Okay. So normally closed contact to the M1 coil, through the normally closed overload contact out to L2. Okay. So let's push that button. Let's operate this control circuit. We'll push the forward button. Push the forward button. So now we have current flow through the forward button, through the normally closed M1 contact, and M2 contact, excuse me, and then we energized coil M1. If we energize coil M1, immediately this seal-in contact closes. So now I've closed this contact, which allows us to have current flow around the forward push button, and I take my finger off the forward push button, and this seal-in contact allows current flow to maintain current to the M1 coil. Okay? And when M1 energizes, this normally closed M1 contact opens. Well, the purpose in that M1 contact is to prevent you from energizing both the forward coil, the M1 coil, and the reverse coil, the M2 coil. Okay? All right, so let's check the state on where we are. We've got the stop button still closed. We've got the M1 contact sealed shut. We've got the M1 coil energized, and we've got this normally closed M1 contact open. All right? And it's just sitting there operating in the forward direction. When I push the stop button, all the current ceases to flow. The M1 coil goes back to the de-energized state. This M1 seal-in opens, and this M1 normally closed contact recloses. Okay, so now we're back to where we started. Now if I push the reverse button, now the current flow will be through the reverse button to the normally closed M1 contact to the M2 coil. M2 seals in right here and opens up this normally closed M2 contact in front of the M1 coil. And now the motor will operate in reverse. And that's a basic forward, reverse, stop circuit. And here's the explanation. When forward is pressed, coil M1 energizes, sealing in around contact M1 around the forward push button, opening the normally closed contact in series with M2, and that prevents both coils from being energized at the same time. The stop's pressed, power flow's interrupted, stopping the motor, dropping out all the contacts. When reverse is pressed, coil M2 energizes, sealing in around contact M2, and then sealing in around the reverse push button, rather, with this contact, and opening the normally closed contact in series with M1, preventing both coils from being energized. Okay. Now, if you look at what are the requirements for energizing either one of the coils, here's what has to be true. First of all, you have to have power on the circuit, all right? So L1 and L2 have to be energized. Okay, and then the stop button can't be pressed and held. Okay, that's one thing. The overloads must be reset, okay, so that this contact has to be closed, otherwise you'll never energize a coil. And if the stop button is not pressed and the overloads are reset properly, and you have power on the control circuit, when you push either one of those push buttons, it's going to work, okay? The forward or reverse push button. Now, three-phase motor circuits. You see a schematic on one here, and typically what you'll do is here. Let's follow the power through first of all. Here's L1 through a power interrupter. That'll be a breaker or a fuse. Let's assume it's a three-phase circuit breaker. Okay, to the main contacts in the starter, through the overload heaters, and to the motor. Okay, each phase through the circuit breaker, to the main contacts, to the overload heaters, to the motor. Okay, so what you'll typically do is take two of those phases. In this case, we're using L2 and L3, and you'll run them through a step-down transformer, control transformer. Okay, and it'll step it down from typically around 480 volts down to 120 volts on the secondary side so that the control system operates at a much lower voltage than the motor operates at. All right, so let's see if we can get this motor started. When I press the start button, the current flows through the start button, through the normally closed stop button, which energizes the M coil. This is the main coil in the motor starter. When M energizes, it closes this seal in around the start button. Okay, that's an auxiliary contact that closes. It also closes these main line contacts and the motor starts running. Okay, so that's exactly how it works. And when I press the stop button, it drops out this coil, which opens this contact, which opens all three of these motor starter contacts. Okay. Now, they left a few things out of the schematic. There's no control circuit fuse. Typically, there's going to be a fuse in this control circuit. And they also left out these overload contacts. We show the overload heaters up here, but we don't have any overload contacts in the control circuit. And they just didn't show them for simplicity's sake. Okay? Now, we're going to stop and take a few minutes break. And while we're taking that break, and we're just going to take a couple of minutes, I want you to think about this. What must be true to energize coil M1? You don't need to send your answers in, but just think about it a minute. What all must be true in order to energize coil M1? That's this coil down here in the bottom rung. What has to happen? What all must be true in order to energize that coil? Well, here's a few things that I thought of that must be true. Well, the fuse F in the top rung has to be good. If the fuse F in the top rung, this fuse right here, is not good, then you're never going to energize coil M1. Also, this push button here, PB1, it can't be pressed. If that push button is pressed, you're never going to energize coil M1. Now, this limit switch right here has to be open. This limit switch has to be open so that CR1 remains de-energized, because if CR1 energizes, it will open this normally closed contact right here. See, so this limit switch has to be open so that CR1 does not energize, so that this contact will remain in its normal state, which is normally closed. Okay? Now, another thing that has to happen to energize M1 is I have to push button PB2. As soon as I push button PB2, it will energize this MCR, Master Control Relay is what that stands for. Okay? When that energizes, it will close this seal in. It will also close this contact. Okay? Now, if this fuse on this bottom rung is good, okay, so that's another condition that must be true to energize coil M1. Coil M1 will energize. Okay? All of that has to be true in order to energize coil M1. All right. Let's talk a little bit about circuit protection devices, fuses, and circuit breakers, used mostly to protect against short circuits. You're going to see either fuses or circuit breakers. What you're looking at here, these pictures are fuse starters. You see the 3 fuses here and 3 fuses here. These are fuse starters. Those are used to protect what's downstream of them from the event of a short circuit. Usually for motor circuits, you're going to want to refer to a table in the National Electrical Code, the NEC, in order to find the full load current for a given motor. Okay, and then you're going to size the current, the elements for the fuse, at 1.75 times the full load current as found in the National Electrical Code table. In other words, you got a 20 horsepower motor. It gives you the nameplate current. But the nameplate current is not what you'll use in order to size the overcurrent device. These are overcurrent devices as opposed to overload devices. The code tells you can size dual element fuses at 1.75 times the full load current. But is it the nameplate full load current, or is it the table value full load current as found in the National Electrical Code? under Article 430, which is motors. In this case, for overcurrent protection fuses, you'll use the table value, which is typically not the same as the nameplate value on the motor, okay? You may find circuit breakers used instead of fuses. Here you see circuit breakers in use to protect what's downstream. Now, if you're going to use an instantaneous trip type of circuit breaker, again, you're going to use the table value, the 430.250 table value of full load current, and you're going to take that full load current and multiply it by 8 to determine what size instantaneous trip circuit breaker you need. Why does it need to be 8 times as great? Well, because the inrush current, the starting current, or the locked rotor current for a typical 3-phase induction motor is about 8 times the full load current. Okay, so in order to get the motor started, if you're going to use an instantaneous trip circuit breaker, you have to make it that much larger. If you're going to use an inverse time circuit breaker, they have delay built into the tripping, so you'll size that at 2.5 times the full load current. And again, that full load current is the table value, not the nameplate value. Now, those are overcurrent protection. What about overload protection? Overloads are generally a result of trying to use a motor inappropriately. You know, if you try to use a 5-horsepower motor to do a 10-horsepower motor's job, then the motor will be in an overloaded situation. It'll try real hard to do 10 horsepower worth of work, and the current will get much, much greater than the motor's designed for, and the motor will either become damaged or it'll go into locked rotor or something will happen. And you know, typically motors can't turn more than the rated amount of work. You can't get more work out of them than they're designed to put out. So what you do to protect against overload is you'll use what's called an overload relay, and these hang right below the starter, right below the contactor as part of the motor starter. And typically electricians have to size the overload heater. The overload heater, of course, is what we saw in that 3-phase circuit. They're in series with the mainline contacts going out to the motors. The load current actually goes through the overload heater. And the National Electrical Code tells us that you'll typically size these depending upon the service factor of the motor, but anywhere between about 1.15 to 1.25 times the full load current, this time found on the motor nameplate. So here's where the motor nameplate full load current comes in when you size the overload heaters. You size the fuses or circuit breakers off a table value. You size the overload heater size off of the motor nameplate full load current value. You may find electronic overloads too. These are getting more and more popular, and typically you don't have to do the 1.15 to the 1.25 multiplier. Usually you'll set the electronic overload right at the motor nameplate full load current. They've got these little dials on the front, and you'll just set it right to the current value, and it'll provide overload protection for your motor. Coordination, circuit coordination, kind of talks about, you know, if you have a fault, you want the next upstream device to clear that fault. You know, if a light bulb blew in your house, you wouldn't want the protective device that would clear that fault to be out on the pole next to the transformer that feeds your house, right? You'd want the circuit breaker that feeds that circuit to trip if a light were to short out in your house. Okay, that's called coordination, where you have the next upstream protective device to trip in the event, or open in the event of a short circuit or failure. And again, the example, light bulb shorts out, you want the 20 amp circuit breaker to trip rather than your main breaker panel or the power company fuse. Let's talk about fault clearing paths. You know, if a fault occurs, you may have thousands of amperes of current flowing until it's cleared. Okay. Now, the National Electrical Code, the NEC, requires you to have a low impedance grounding bonding path back to the source for motor circuits, in case you were to have a phase go short to the raceway. Okay, which typically the raceway for motor circuits is conduit or cable tray. Now, rigid metallic conduit can serve as the grounding bonding path. Okay, it can serve as the low impedance path for a motor. Rigid metallic conduit can. So can EMT, electrical metallic tubing, sometimes called thin wall conduit. Sometimes IMC is used, intermediate metallic conduit. That can also serve as a low impedance path. But if you're going to run the circuit conductors in PVC conduit or fiberglass conduit or some kind of an insulating conduit, you have to pull a fourth conductor, which will either be bare copper or it'll be green insulation is allowed, and that will serve as the fault clearing low impedance path. All right, let's move on to transformers. What are transformers? Well, they're power transfer devices. That means that the power in to the transformer on the primary side equals the power out on the secondary side, and that's assuming that the transformer is lossless. And that's not really a bad assumption. Transformers are pretty efficient. They do get a little bit warm. There's a little bit of losses in transformers, but for the most part, a large transformer, you can neglect those losses and say power in equals power out. Okay, so in other words, voltage in times current in equals voltage out times current out. So, you know, if you look at that equation, you can see that if you decrease the voltage from input to output, then the current is going to increase from input to output because VI equals VI. So if it's a step-down transformer, step down meaning that you have a higher input voltage than secondary voltage, then it'll be a step-up current. In other words, the secondary current will be much greater than the primary current. Now, if it has a lower primary voltage than the secondary voltage, so the secondary voltage is higher than the primary voltage, that's called a step-up voltage transformer. Okay, step up, step down from primary to secondary according to what the voltage does. You know, there's many different types of transformers. We're just going to cover a few of them. This is the type of transformer that the utility company will hang out on the pole in front of your house. It's a single-phase, step-down distribution transformer. You see the one on the left. Schematically, here it is right in the middle of the page. This one has a 4160-volt primary, 4,160-volt primary. That would be on these bushings right here. And that's a typical distribution voltage around a subdivision, typically. And on the secondary side, this is a single-phase transformer. It has two phases, and then there's a center-tapped neutral, which is grounded, establishing the neutral. That's called the grounded conductor. So this is, you know, what they run into your house. You'll have 120 volts reference to ground or the center tap on both phases, 240 volts phase to phase. So that's a single-phase transformer. On the right, you see a control transformer. We talked about control transformers a little bit earlier. This is a single-phase step-down control transformer, such as what you'd use, you know, if you had a 480-volt motor circuit and you wanted 120 volt control. You'd use a little control transformer like this. Three-phase transformers, you're going to find them in one or two different configurations. They're either going to be delta or Y. And you look at the delta connection on the left, you see three different windings. That may be made up of three different single-phase transformers. You can connect three single-phase transformers into a three-phase delta. The one on the right is a Y connection or star connection, where you form the center of the star. And again, it can be made up of three single-phase transformers, or it may actually be what's called a three-phase transformer, which is basically three single-phase transformers in one box. Okay, it forms a three-phase transformer. You know, the secondary and the primary can be connected into a delta or a Y. So there are really only four different configurations you're going to see on three-phase transformers. You'd be in YY, Y primary, Y secondary. Or you may have a delta primary and a Y secondary. You may have a Y primary and a delta secondary, or maybe both of them are delta, okay, which would be delta-delta. And on the page there, you see a delta-connected primary on the left and a Y-connected secondary on the right. And then over here on the right, this is how it would be actually physically connected. You have three single-phase transformers. We need to connect the primary up here on the top, the ABCs up here on the top, the capital ABCs. We need to connect them into a delta connection. In order to make a delta, I just need to connect them all in one big loop. So we come in here, there's a connection, H1, H2, H1, H2. So you can see that just all the way around into a delta, the same way over here, all the way around into a delta, okay? That's the delta primary. And then we need to make a Y connection on the secondary side. And right here is the center of the star where all the X2s are connected together right here. X2 to X2 to X2, and then X1, X1, X1 forms my ABC output phases for the secondary. So that's a delta Y transformer connection. Now, one interesting thing about a delta connection on transformers, you can actually make the connection with two transformers. Or if one of the transformers burns up, either on the primary or secondary, it'll still operate and it'll still put out power. This is called an open delta configuration. You can't get as much power out of an open delta as you can out of a three-phase delta, a three-transformer delta. However, you get about 57.7% of the power of a three-phase delta connection. And you can see there's two transformers here. There's the primary connection, there's a secondary connection, two transformers connected into an open delta, and you bring in three phases in the primary and bring out three phases on the secondary. And there they are, open delta. You can actually build a delta three-phase system using two transformers. All right, I want to stop there just a second and check for any questions, see if anybody has asked any questions, and seeing none. At this time, I'm going to continue on. Folks, if you want to ask any questions between now and the end of this seminar, feel free to put them in the question box, and we'll get to them at the end of the presentation. We need to talk a little bit about electronics. Electronics is a very, very deep, complicated subject, so I'm not going to be able to get into it very, very much, but we are going to cover just a little bit of the basics of electronics. The first thing I want to do is just look at a few of the components that are used in electronic circuits. In the upper left-hand corner, you see what's called a bipolar transistor. It consists of three leads. There's an emitter, a base, and a collector. And the one on the upper left is called a PNP bipolar transistor. The way I can remember that, PNP, I think of pointing in, pointing, and the arrow on the emitter is pointing in. Notice it's pointing in toward the base. So that's a PNP bipolar transistor. It consists of collector, base, and emitter, and the arrow is pointing in. Okay, so that's a PNP. As opposed to the one on the right, this is another bipolar transistor which has a collector, base, and emitter, and this time the arrow is shown pointing out. So I say that's NPN, not pointing in. NPN, not pointing in. That's how I remember it. The difference between PNP and NPN is how the doped substrates are layered. The PNP has a positive doped substrate, and then a negative base substrate, and then a positive based, and just the opposite on the NPN, negative, positive, negative. That's how the transistor is constructed. Okay. So again, PNP, pointing in, pointing, NPN, not pointing in. That's how I remember it. We looked at diodes in circuits a little while ago. That's what a diode physically looks like, a little black round thing around. It kind of looks like it's wrapped around the wire. You see the line? The line on the diode represents the schematic line, okay, which determines the direction of current flow for that diode. And then in the lower right, you see SCRs. SCRs, silicon-controlled rectifiers. See them schematically. They consist of an anode and cathode and a gate. These are like electronic switches. They're usually high-current electronic switchers, SCRs. And one of the interesting characteristics about an SCR is if an SCR fails, it'll fail to the shorted condition. It won't fail to the open condition. It'll fail shorted so the current always flows. The way they typically operate is you have to have a gate at a certain voltage level for these things to conduct at all. They're like a switch. Okay, they rectify, but they're not really often used as a rectifier. They're used more as a switch. And when the gate is at a certain voltage, they'll conduct. And when the SCR fails, usually they'll fail to the shorted condition so that they conduct all the time. Now, we looked at full-wave bridge rectifiers a minute ago. I thought we'd take another look here now that we're talking about electronics. If you take an AC waveform, as shown here on the left, run it through a transformer, step it down in voltage level if you want, and then run it through what's called a full-wave bridge rectifier consisting of 4 diodes, 4 rectifiers. And then you take the output across that resistor right in the middle, okay? So you're going to measure the output right at that little resistor in the center of the diode bridge. You're going to have a full-wave rectified AC waveform which turns into a pulsing DC waveform. Okay, the pulsing DC waveform is a rectified, full wave rectified AC waveform. On the left is a special type of a diode. These are called Zener diodes, and they operate in reverse bias. Reverse bias meaning that they operate kind of in the different area than a standard diode would, which diodes normally conduct only in the forward bias direction. They operate over here in this region of the curve called the breakdown voltage. And the characteristic of a Zener diode is once it reaches the breakdown voltage, it'll clamp that voltage regardless of how much current flows. It'll look like a voltage regulator, and that's what they're often used for. Okay. Schematically, you see they've got anode, cathode, and this little squiggly line right here means it's a Zener diode. And over here on the right, I wanted to look at a Zener regulated power supply. You could build this thing and it would work pretty well as a regulated power supply. It doesn't require a transformer to have 110 volt AC to plug in the wall and get about a 5 volt output. Okay, you can do that without a transformer using this little regulated power supply. So let's kind of schematically see what's going on. We've got 110 volts of AC power applied through a fuse, through a 5-watt resistor. That's the guy that drops a lot of the voltage right there. Okay, it's 10 k ohms, 5-watt resistor. That's your heat source. It's going to drop a lot of the rest of the voltage is going to drop right there. Okay. Then you go into this diode bridge. That's just a full wave bridge rectifier using standard diodes. Then we come back out to a capacitor. The capacitor doesn't really serve a major function in the explanation of this circuit. If you look at the output of the bridge, now this is going to be a pulsating AC wave, pulsating DC waveform, okay, full wave rectified DC waveform. I can clamp that voltage at 5.1 volts by using a Zener diode with a breakdown voltage of 5.1 volts, okay? So that means nothing's going to get past that diode greater than 5.1 volts. So I've got 5.1 volts of pulsing waveform going out and feeding this capacitor right here, and that capacitor is going to smooth it all out. That's a filter capacitor. It's going to smooth it out and leave me with an output here of roughly 5 to 5.1 volts of fairly steady state DC. Okay, so that's what this regulated power supply is. All right, let's take a look at some combinational logic circuits. Now, these may be drawn different than you've seen them in the past, but this is the way they're usually portrayed in the civilian world and industry. And we're just going to look at a few of the most common logic gates. There's a lot of different logic gates that are used to make combinational logic circuits. But we're going to look at these 5, the AND, the NAND, the NOT, the NOR, and the OR. Those are five of the most common ones. Let's take a look at them in terms of how do they function. The outputs of these gates are defined as follows. The AND gate. The AND gate, looking back at this, the AND gate is this guy right here. It's got a flat back and then a rounded front. An AND gate, for the output to be high, it requires all of the inputs to be high. If there's 2 inputs or 3 inputs or 4 inputs, whatever inputs number that AND gate has, all of them have to be high, a 1 state, as opposed to a low, which we call the 0 state. They have to be high in order to get a high output for the AND. Now, for the OR gate, again, the OR now has the rounded back, and then it kind of comes to a point up here in the front. That's the OR gate. An OR gate, in order to get a high output, it requires one of the inputs to be high. Okay, any of them can be high. If any of the inputs are high, whether they be 2, 3, 4, 5, 10 inputs, whatever, as long as one of them is a 1, you're going to have a 1 output. Okay, that's the characteristic of an OR gate. Now, the NAND and the NOR are just the opposite of the AND and the OR. Okay, a NAND is a not AND. So if an AND requires all the inputs to be high for a high output, then the NAND is going to say that the output is going to be high for all combinations of inputs except when all of them are high. Okay, and we'll look at this in the truth table format in just a minute. But I just wanted to kind of talk about it a little bit. The output is going to be high for any possible input combination except when all of them are 1. Okay, that's the NAND. NOR is just the opposite of the OR. It's a not OR. So the output is going to be low anytime you have a high input. Just the opposite of the OR. And the NOT is an inverter. It takes a high input and turns it into a low output, takes a low input, turns it into a high output. And those are how those logic gates work. And let's look at them in terms of a truth table. The AND gate, let's look at just two input ANDs, okay? Here's all the possible combinations of inputs for an AND gate. 0011, 0101. Those are all the possible combinations of inputs for a two-input device. Now, an AND gate only has a 1 output when both inputs are 1. So I've got a 00 input is going to produce a 0 output. A 01 input going to produce a 0 output. A 10 input will produce a 0 output. And here we've got a 11 input. All the inputs are high, so now my AND gate is a 1. Okay, my output is a 1. Okay, that's the two-input AND. If we look at the two-input OR, anytime I've got a 1 in any of the inputs, it's going to produce a 1 output. So the only case that I don't have a 1 in one of the inputs is a 00 input case. And that produces a 0 output. Here I got a 1 input, so it got a 1 output. Here I've got a 1 input, it's got a 1 output. Here I've got a 1 input, that's a 1 output. So that's the truth table for a two-input OR gate. Let's look at the NAND. Now the NAND is just the opposite of the AND. You remember, the AND gate we said we had to have a 1 input for a 1 output. So now for the NAND, we've got a 1 input produces a 0 output, and any other input combination produces a 1 output. So a 00 input for a NAND gate produces a 1 output. A 01 input produces a 1. A 10 produces a 1. And the 11 produces a 0. So there's the truth table for a two-input NAND. NOR is just the opposite of the OR. The only time I have a 1 output is if I don't have any 1 inputs. So 00 input will produce the 1 output. Here I've got a 1 input, so that's going to produce a 0 output. Here I've got a 1 input, that's going to produce a 0 output. And the 1 input will also produce a 0 output. So there's the two-input NOR gate. Truth table. Now, I thought we'd work through a little combinational logic circuit example here. We have 3 inputs, a W, a P, and a D. We've also got 3 gates. We've got this inverter gate, this inverter gate right here, the NOT gate. We've got an AND gate, and we've got an OR gate, and they're kind of stacked together there in order to produce an output out here at the final end. What we need to do is find out what is this output in terms of all the possible combinations of inputs. Okay, so we're going to work through this circuit, and we're going to do it a step at a time. Okay, so step 1 is we need to make a table of all the possible combinations of input. Well, the inputs are D, P, and W, D, P, and W. So there's 3 different inputs, and we need to make a table of all the possible combinations of those inputs. And the easiest way to do that is to take one of them and just go 0, 1, 0, 1, 0, 1, 0, 1, and then go 0, 0, 1, 1, 0, 0, 1, 1. And then the W will be 0, 0, 0, 0, 1, 1, 1, 1. And that is all the possible combinations. There's 8 of them, 8 possible combinations. You can determine the number of possible combinations by 2 raised to the power of the number of inputs. So 2 to the third is 8. There's 3 inputs. 2 to the third is 8. So there's 8 possible combinations of input, and there they all are. Step 1, make a table of all possible combinations of inputs. All right, now, step 2, let's identify the output of this NOT gate right here. I need to know what that NOT gate is relative to the D input. Well, it's going to be just the opposite of the D input. So I move my table over a little bit and stick another column in here for A, which I call A, the output of that NOT gate. So whenever D is a 0, A is a 1. The output of the NOT gate is a 1. Whenever D is a 1, A is a 0. Okay, so there's the output of the NOT gate, which is the inversion or the opposite of D. And I put that column right next to D, which will simplify things nicely here in the end, okay? Next step. Let's identify the output of this AND gate right here. And this AND gate I label point B. Okay? I want to find out what is point B relative to all its possible input combinations. Well, its possible input combinations are A and P. A and P feed that AND gate. B is its output. So now I'm looking at all possible combinations of A and P, and anywhere I've got a 1, 1, I'm going to have a high output. So there's a 1, 0, that produces a 0 output. There's a 0, 0, that produces a 0 output. Third line down, I've got a 1, 1, that produces a 1 output. There it is, 1, 1 produces a 1 output. 0, 1 is a 0. 1, 0 is a 0. 0, 0 is a 0. Here's another one, 1, 1. ANDed gives me a 1. 0, 1 ANDed gives me a 0. So there's the output of the AND gate relative to all its possible input combinations. Step 4, we're going to find the output, C. I label that point C. Now, C is the output of an OR gate. What's being ORed together? W and B are the inputs into that OR gate. So I want to OR W and B. So any time W or B is a 1, I'm going to have one output. Every other combination will be a 0. So let's see. Here's a 0, 0. That'll be a 0. Second row, 0, 0. That produces a 0. Third row, 0, 1 produces a 1 output. Fourth row, 0, 0 produces a 0. And in 5, 6, 7, and 8, I've got a 1 output, 1 input. So all of those are going to produce a 1 output. So there is the output C relative to all the possible combinations of input D, P, and W. And we've solved that combinational logic circuit. Let's go on and take a look now at PLCs and ladder logic circuits. Programmable logic controllers, or PLCs for short. Most often these things consist of input and output modules. They have some sort of CPU, central processing unit, or computer. They have a power supply, and then they got some kind of a rack with a powered backplane that holds all the above and powers them up. Okay, that's a typical PLC. You see a picture of one on the right there. Okay, PLCs are used a lot in industry. You know, they're used to control industrial processes, to control equipment, and to control how machinery operates. The new PLCs can do true process control. They can take analog inputs, which is a constantly varying signal, such as from a pressure transmitter or temperature or flow, and then it can produce outputs such as valve position, motor speed, or some other functionality. It can actually do process control, variable inputs, variable outputs. Okay, and formerly this was a function only of distributed control systems, DCS systems, but now PLCs can do this too. Okay. How do they operate? Well, PLCs, CPUs, what they do is perform what's called a scan of the relay ladder logic. The status of the inputs determines the outputs for a PLC. Well, that's the same with real relay logic. You know, the status of the input of the relay determines the output. Relay ladder logic, sometimes called RLL, is combinational. It's made up of combinations of devices, and it's sequential because the PLC operates with the scan. It'll start at the top of the program, and it'll work its way all the way down to the bottom. When it gets down to the bottom, it'll go back up to the top and scan again. That's how PLCs operate. Now, relay ladder logic kind of simulates real relay action by using virtual relays, and it performs these logic functions. Okay. Let's look at this is out of a real PLC. This is some relay ladder logic. It consists of input contacts, and these might be wired to switches or some kind of a device that turns on and off. Okay, and then depending upon the status of the input, will determine how the outputs work. Okay, and these outputs are represented as coils, and coils can have auxiliary contacts associated with them, but then there's some kind of a real device associated with that output. It may be a light or whatever. It may be a motor starter. You don't know what the outputs are unless you get into the program and determine that. But, they consist of these input contacts and output coils, and there are also auxiliary contacts associated with the output coils, just like a real relay. Let's take a look at this little device right here, this little I/O circuit. I've given you an input module on the left, an output module on the right, and I've given you a schematic over here on the right, relay ladder logic on the right. Okay, this is relay ladder logic. And let's see if we can figure out how this operates. Okay, I've got 4 normally open push buttons feeding input modules points X1, X2, X3, and X4. All of those go into the input module. Okay, they're normally open push buttons. And then I come out of the output with these coils. Okay. Let's see if we can figure out how this operates. Well, let's see. If I were to press X1, if I were to push that button X1, that's going to close this contact over here in the top rung of the relay ladder logic. As soon as I close that contact, it's going to energize coil Y1, this physical coil Y1 on the output module. Okay, and that's going to seal in around X1, and it'll remain energized. Okay, it'll remain energized. It'll also, let's see, is it going to do anything? Yeah, it's going to open up this contact right down here, right? It's going to open up this contact, this normally closed contact. As soon as Y1 coil energizes, it opens up this normally closed Y1 contact. Okay, so that Y2 can never get energized. Okay, what if I were to press X3 while it was in that state with Y1 energized? As soon as I press X3, this contact here opens, which drops that coil Y1, which drops at the seal in, which closes this normally closed contact back. Okay, so Y1's de-energized at that point. Suppose I press X2. Contact it. The input module senses a change in X2 and closes this contact X2, which energizes coil Y2, which closes this auxiliary contact for Y2 down here on the bottom rung and opens up this normally closed contact here for Y2, you see. And Y2 remains energized until I press X4. As soon as I press X4, it opens up this normally closed contact in the relay ladder logic, which breaks current flow to Y2, breaks the power flow to Y2, which opens up this auxiliary contact and closes back this normally closed contact. What is that circuit? It's exactly the same circuit as we looked at earlier in terms of a forward-reverse start-stop circuit, okay, start circuit. Forward-reverse motor starter circuit, in other words, right? Now, it looks a little bit weird here because all of the contacts are shown in the normally open state. But see, you can do that with normally open buttons if you've got contacts that you can place in either condition. You program this contact rather to be normally closed. See, this is the stop contact for the Y1. This is the stop contact for Y2. And you program them normally closed, then you can use a normally open push button to operate them. Okay? So that's just a forward-reverse motor starter circuit. That's all that is. Now, modern PLCs also contain what are called functional blocks, and these functional blocks do a whole variety of tasks. You can get functional blocks that will do timers, counters. You can get mathematical operating functional blocks. You can get what's called one-shot functional blocks. They'll fire once, and then that's it. You can get latches, latch functional blocks. You can get all kinds of control functions like integration and derivative control, PID control. There's a lot of different types of functionality that is built into modern PLCs. You can really, really do a lot with them. And sometimes the programming can get very, very complicated as well. They send you to school generally to program a PLC. Now we're going to talk a little bit about conductors, just conductors for general wiring. Wires. When a wire number decreases, going from a 4 AUG, and AUG, by the way, AUG stands for American Wire Gauge. So if I go from a 4 AUG to a 2 AUG wire, if I go down in number from 4 to 2, that means the ampacity, which is how much current flow can go through the conductor, and the size of the conductor both go up. So a 4 is smaller than a 2. And I can get less ampacity, less conductance through the 4 than I can through the 2. Now, how much ampacity can I get through the wires? You look it up in the National Electrical Code. There's a code, there's a table in the code under Article 310. Conductors for general wiring is the title for Article 310. And there's a table in there, 310.15b16, which gives you the ampacity of conductors. Tells you how much current can flow through those conductors. Now, if you use that table, it's important. The table is made up of many different types of conductors, aluminum and copper, but the main column headings are temperature. Okay, there's a 60 C column, a 75 C column, and a 90 C column. And to determine the ampacity of a conductor, you'll generally read the ampacity off the 75 C column, and that's regardless of the type of insulation. There's many different types of insulation that they place on conductors. Some of it's 60 insulation, some of it's 75, some of it's 90. Some of the most common wiring is 90 C insulation, but you'll typically read that off the 75 C column because it's not the insulation type that ends up determining the temperature rating of the circuit. It's the terminations. Terminations are rated at 75 C maximum. Okay, terminations being, how do you end the wire in a lug, in some kind of a squeeze connector, or what's going to allow current to flow into the wire is the termination. And the highest rating of those terminations, 75 C, and that really limits the ampacity of the circuit. Because if you look in the difference between the 75 and the 90 C column in this National Electrical Code table, you'll find that the ampacity is always greater in the 90 C column than it is in the 75 C column. And you might say, well, why would I ever need the 90 C column? Well, you need the 90 C column anytime you do what's called adjustments and corrections. Adjustments and corrections are used to change the ampacity of the conductors. And some of the reasons you need to change that ampacity of the conductors shown in that table is if there's more than 3 current carrying conductors in a conduit. If you take a conduit and put 6 current carrying conductors in it, then you have to adjust the ampacity of those conductors, which means you can't put as much current flow through them, okay, because they'll get too warm. Ambient temperature. If you're up in the top of a really hot building with a conduit, wire in it, it's 120 degrees, 130 degrees up there, you have to adjust the ampacity of that conductor due to ambient temperature. You also have to adjust in rooftop applications where the sunlight shines on the raceway. And these adjustments and corrections typically make the current carrying capability of the conductor less than the table ampacity values. The exception being, I mentioned ambient temperature. If you were to install electrical wiring in a freezer or up in northern Alaska, then the ambient temperature adjustment would allow you actually to put more current flow through that conductor than the table 310.15b16 values. Okay? I mentioned this a little bit earlier about testing cables, insulation of conductors and of motors and anything that's got insulation in it is tested using what's called a megger. Megger is short for megometer. And you see a couple of pictures of meggers there. The one on the left is a hand crank megger. That's a 500-volt megger. The one on the right is a battery-powered megger, and it actually puts 1,000 volts out. Okay, and you can have a couple of leads that come out of this megger, and you attach them to the conductor and the surrounding raceway, and then you energize the megger by cranking the handle or pushing the button, and that introduces a large voltage. The megger is a very sensitive current measuring device. It measures how much current actually flows. And then it does an Ohm's law calculation to determine how many megohms of resistance times 10 to the 6th ohms of resistance there are between the conductor and its raceway. Okay, so that's how you test conductors using a megger. All right? Have to be real careful with meggers too, because 500 volts or 1,000 volts can be very harmful to you. So always make certain that you use voltage-rated gloves whenever you use meggers. Now, this last section here I want to talk about is some basic electrical equations. I think you'll find some of these useful just as a reminder, okay? First of all, Ohm's law. Ohm's law in its basic form says voltage equals current times resistance. And you can, convolute that equation to say I is equal to V over R, or R is equal to V over I. And Ohm's law applies to both AC and DC. However, if you're going to use an AC, it's not R, it's Z, or it's the total impedance rather than the resistance. Okay. The basic single-phase power equation, power is equal to voltage times current. Power in watts is equal to the voltage in volts times current in amps. Now, the three-phase power equation is shown here. The true power meaning the amount of work you can get out of the equation, the amount of heat that you get out of a resistor. True power is equal to the square root of 3 times line voltage times line current times the power factor. And the power factor is the cosine of the phase angle difference between voltage and current. The phase angle difference, the cosine of the phase angle difference between voltage and current is the power factor. It's kind of a relative measure with how much in phase the voltage and current are. If they're both in phase with each other, power factor is 1. If they're out of phase with each other, then it's something less than 1. Okay. So those are a few equations just to remind you of, and here's a few abbreviations that you need to keep in mind. Milliamps or milliwatts or millihenries is 1/1000th, 10 to the minus third. Micro is 10 to the minus sixth or 1/1,000,000th. Kilo in kilowatts or whatever is 1,000, 10 to the third. And meg is 1,000,000 or 10 to the sixth. Those are some of the more common abbreviations you need to be aware of. I wanted to just go over quickly a little bit of triangle math with you as well. Okay, you see a triangle there on the right side of your page. Relative to angle capital A, the adjacent side relative to angle A is called side little c. The opposite side is called side little a. And the hypotenuse, the longest side of the triangle, is side little b. Okay, and those are all the sides of the triangle, and those are all relative to angle A. Now, the Pythagorean theorem shows you that the side B, the hypotenuse, is equal to the square root of the sum of the squares of the opposite and the adjacent side. So B is equal to the square root. That's a total square root there. That's supposed to be a radical over that whole a squared plus c squared. B is equal to the square root of a squared plus c squared. So if you need to know the length of the hypotenuse, you can use the Pythagorean theorem if you know the opposite and adjacent side length by squaring the two sides, adding them together, and then taking the square root of it. Okay, and that'll give you the adjacent side, the hypotenuse side angle, which is side B. Now, if you only know the angle A, you know the angle in degrees, A, and you know the lengths of some sides, maybe one side. You maybe know the angle and you know one of the sides. You know everything there is to know about the triangle because of the trigonometric functions sine, cosine, and tangent. Okay? The side of the angle A, sine of the angle A is equal to the opposite over the hypotenuse, A over B. The cosine of angle A is equal to the adjacent over the hypotenuse, C over B, and the tangent is equal to the opposite over the adjacent, A over C. Now, I don't memorize a whole lot of stuff. I'd rather remember some kind of a little mnemonic or something that gets me all the answers. So what I remember on the trigonometric functions is this word here, SOHCAHTOA, S-O-H-C-A-H-T-O-A, SOHCAHTOA. SOHCAHTOA sounds like an Indian word, right? SOHCAHTOA. Now, how does SOHCAHTOA help you remember the trigonometric functions? It's very simple. S, sine, is equal to opposite over hypotenuse. That's so. Sine is equal to opposite over hypotenuse. Ca, C-A-H, cosine is equal to the adjacent over hypotenuse. Okay, cosine equals adjacent over hypotenuse. And then TOA, tangent, equals opposite over adjacent. So what I'll do if I'm going to work a problem and I come across something that requires trigonometric functions is I'll just write SOHCAHTOA on the page, and from that I'll be able to get sine, cosine, and tangent functions. Okay, it tells me everything I need. That one silly word tells me everything I need to remember all the trigonometric functions that I need in order to solve a right triangle problem. Okay, let's work an example of where it may be needed to remember a little bit about trigonometry. It's kind of a real world problem. You know, you're working in a plant, and you need to run a new conduit. Okay, and you need to match up with an existing conduit rack. Okay, and there's an offset in that existing conduit rack, and you need to match it. Okay, and you determine with a protractor that the angle for the offset is 38 degrees. 38 degrees is how much the angle needs to be. And you take your ruler and you measure the distance of the offset is going to be 32 inches. So you know the angle and you know the distance between, you know how much offset you need. But what you don't know is how to set up the bender. You know, with a bender you usually put marks on the conduit, and you make the first bend, then you turn it over and go to the next bend, and bend the same angle, and you'll end up with an offset, right? So what do we know again? We know the angle, 38 degrees, and we know in terms of a triangle, if you can imagine making a triangle there where 38 degrees is the angle, and you know the height of the opposite side, which is 32 inches. And you need to know the distance between the marks. That's what you're looking for, which is the length of the hypotenuse. So you know the angle, you know the opposite side, 32 inches, and you're solving for the length of the hypotenuse. Okay, so if I was confronted with that, I would write SOHCAHTOA, right? Let's see, sine is opposite over hypotenuse. Well, glory be. I know the angle, so I can find the sine of the angle with my calculator. I know the opposite side, and I'm solving for the hypotenuse. So, S-O-H, is what the function I need to use. The sine function is the one I need to use. The sine of the angle is equal to 32 inches divided by the hypotenuse, A. Sine of 38 is equal to the opposite side, 32 inches, divided by the hypotenuse, which is what I'm solving for. I take that equation and solve it for the hypotenuse, A. And if you do that, you get the hypotenuse, the length of the hypotenuse, A, is equal to 32 inches divided by the sine of 38 degrees. And you plug that into your calculator, 32 divided by sine 38. Make sure your calculator is in degrees and not radians, of course. And you come up with 52 inches. What that tells me is that if I place bending marks 52 inches apart to line up with the bender, if I bend that angle at 38 degrees, I'm going to end up with an offset of 32 inches, which is exactly what I wanted. I bend 52 inches between the marks, 38 degrees, and I end up with a 32-inch offset, and I matched the rack perfectly. All right? So there's a real-world example where triangle math really saves the day. All right. I want to mention a little bit about electrical safety. Guys, the electrical world and industry is changing dramatically. There's a document called NFPA 70E, the Standard for Electrical Safety in the Workplace. 2012 edition is the latest edition of this document, put out by NFPA, National Fire Protection Association, the same people that published the National Electrical Code that I referred to earlier. This book helps us to work safely around the hazards of electricity. The main hazards of electricity are shock and electrocution, which is defined as shock that results in death. If you die from shock, it's an electrocution. Okay? And arc flash. Arc flash is a significant hazard because of the high temperatures and blast forces involved in an arc flash event. NFPA 70E gives us some strong recommendations of how we can work in the trade for many, many years and not get hurt from shock or die from electrocution or get arc flash burned. And most responsible companies expect their electricians to follow proper electrical safety rules. So here's a few of them that you need to be aware of if you're going to do voltage testing or you're going to do troubleshooting on equipment and there are voltage over 120 volts. You need to be aware that arc flash could be a hazard if the voltmeter were to short. And what I mean is, what do you do with the voltmeter? You take that meter and you place it phase to phase. You place it phase to ground. You're testing, performing diagnostics. Maybe testing as part of lockout tagout for lack of voltage. If there's anything wrong with that voltmeter, it can initiate an arc flash. So voltage testing as part of lock and tag is a very necessary safety step. It's also a dangerous act. Okay. So arc flash can be a hazard when you're using a voltmeter, So typically, anytime you're using a voltmeter with voltages over 120 volts, you're going to be wearing arc flash protective clothing. Okay. Shock and electrocution are also a hazard. You've got a meter in your hands. You're around hazardous voltages. If something goes wrong, you could contact the energized part and you could get shocked or even electrocuted. So arc flash and shock and electrocution are hazards for higher voltage equipment in general. Now, if you're going to be testing or troubleshooting on lower voltages, typically arc flash is not the hazard. However, shock and electrocution are a hazard any voltages over 50 volts. 120 volts may seem to some of you like a low voltage, but it's a fact that more people die from 120 volt shock than any other voltage. Why? Because obviously it's more common than other voltages. Okay, here's what we're talking about for doing voltage testing in the industry nowadays in a motor starter. Okay, this guy's doing a voltage test in a motor starter. He has on voltage-rated gloves. That's the leather gloves you see. Has leather over protectors on over top of those. The leather protects the rubber voltage-rated glove. He has on arc-rated clothing. That's that blue suit he's wearing. Has a face shield, an arc-rated face shield, so that if an arc flash were to occur, his face wouldn't get burned up. Has on a plastic hard hat. He has on safety glasses, has on earplugs, and he has on protection for the back of his head, in this case a hood. This is the typical dress in industry now for doing voltage testing in a motor starter. Okay, here's some more pictures of guys going to work in electrical equipment, right? Again, this fellow's wearing a balaclava, an arc-rated balaclava or sock hood to protect the back of his head. He has the face shield, safety glasses, earplugs. Why earplugs? To protect your ears from bursting if an arc flash were to occur. The pressure wave is so great from an arc flash that your eardrums will burst. Okay. Again, this guy has on the arc-rated clothing. He has voltage-rated gloves, has on leather over protectors, and he's using a good quality voltmeter. He's ready to go to work on energized electric equipment. Here's what we're talking about. This is an arc flash occurring. With no more PPE than this guy has on, he could get badly burned from that arc flash. And here's another arc flash event. See the heat and the plasma coming out, hitting the guy right in the chest. He's got on a cotton T-shirt. He does have a face shield on, but it's not an arc-rated face shield, so more than likely this non-arc-rated face shield is going to melt and burn. His T-shirt will catch on fire, and he'll have vast body burns. He may not even survive. I mentioned voltage testing. Most companies require voltage testing to be a three-step process because of the fact that voltmeters fail, sometimes at the least opportune time. Voltage testing is a three-step process where you test the voltage tester in a known live circuit. A good known live circuit is a wall outlet, like a 120-volt wall outlet. Make sure it's working properly. And then you perform the voltage test. This is critical if voltage testing is part of your lockout tagout. You need to know the meter's working properly before you do the voltage test for lockout tagout. So you test the tester, you perform the voltage test, and then you retest the tester in that same known live circuit to verify it's still working. And again, anytime you're working on voltages over 50 volts, in industry now, you're expected to wear shock protection, which is voltage-rated gloves and leather over protectors. General rule in industry now is de-energize the equipment unless there's no way you can work on it. And troubleshooting is an exception, of course. A lot of times you have to leave the equipment energized to troubleshoot. But if there's any way you can de-energize it, that's the expectation. If you can't de-energize it, you've got to do whatever it takes, including wearing the proper PPE, to protect yourself from the hazards of the job. And always, always, always test before touch on anything that could be energized. Okay, we've come to the end of the webinar on electrical and basic electronic review. Hope you've enjoyed it. Hope you found it informative. Let me see if we've got any questions to answer before we sign off. Okay, I've got one here. Will there be another webinar before the testing and interviews? I can't answer that. I really don't know the answer to that. You may be able to contact the person you're working with at Orion. They might be able to tell you if there's going to be any other webinars before your testing interviews. I really don't know the answer to that, sir. I'm sorry. I appreciate you folks that are thanking me for my time and assistance. I Hope it has been informative. Here's a question about graphing calculators. I'm sorry, I'm not the person to ask about calculator use during the test. I don't know what type of calculators you're allowed to use, if any. Okay, so again, contact your Orion rep, and they ought to be able to help you figure out what type of calculators are allowed, what you can use and what you can't use when you're taking your test. Let's see, I think that's the last question. Well, folks, I've enjoyed talking to you. It's been a one-way conversation, but I hope you've learned something, maybe a little refresher anyway, kind of jogged your memory on some things that you knew before. I wish you the best of luck. Thank you for serving your country. God bless you. And I'm going to sign us off right now.